There's only 3 pieces past the flag.
Hello.
Okay. I guess we can get started. Let me share my screen. Okay. Can you see my screen?
Yes, we can see it.
Wonderful. Okay. Last time we talked about high frequency solutions. We talked about tangent plane approximations for Math's principle and generalized Snell's law. Today I'm going to talk about Gaussian beams. Gaussian beams are a kind of beam that you can use to describe light rays. And it's pretty effective, like describing a laser beam. Okay, so let me see. So the first thing we should know about is something called the paraxial wave approximation before we study Gaussian beam. So what is paraxial wave approximation? We can think of it this way, that if you have a waveguide, let's assume that we have a parallel plate waveguide. We never talked about parallel plate waveguide in this course, but we did talk about rectangular waveguides. Parallel plate waveguides are in fact simpler than rectangular waveguide. And what you have is two metallic plates. And if the waves have to bounce off the metallic plate, that's how the wave looks like. You can think of the wave as being bouncing plane waves back and forth between the two parallel plates. And then the k vector is pointing in this direction, or you can call it beta vector as well. So as the frequency gets higher, k is the length that is omega over c. Okay, or the beta, you can also call it beta vector if you want to. It has a length of omega over c. So as the frequency gets very high, in order for the k vector to fit into the waveguide, the wave has to bounce more or less like this. Okay? So you can see that the wave bounces more parallel to the surface now because of the increasing frequency, the increasing length of the k vector. Okay? The component of the k vector is pretty much the same. It might be like pi over a. Okay, beta x might be pi over a. In this direction, if I call this the x direction. So if you solve for the discretization of the beta x, it would be pi over a, or n pi over a, or m pi over a if you wish to. But it is supposed to be fixed. And as you increase the frequency, the k vector becomes more and more horizontal. And then eventually, when the frequency is extremely high, the k vector is essentially parallel to the axis. Okay, this is the axis, and this wave is called a paraxial wave. So a paraxial wave is a wave that is propagating almost parallel to the x-axis, or in this case, the z-axis. We can call this the z-axis, for instance. Okay, so let's look for the solution of the wave equation when the frequency is very high. So in order to do that, we can study this vector wave equation for vector potential. We know that when the frequency is very high, or irrespective of what the frequency is, the vector potential satisfies this equation. Okay, for source-free medium. Then we also know that there's a scalar potential that is associated with this, and that scalar potential is given by this equation over here. Both of them are source-free, so there are no source on the right-hand side. And we further know that in order to solve these equations, we need a Lorentz gauge, which is given by this, which is called the Lorentz gauge. Lorentz without the T. Okay, so we're going to look for a paraxial wave approximation to this equation. So what we're going to assume is that the vector potential A will consist of two parts. One is slowly varying part plus a rapidly varying part. Okay, so this is rapidly varying. This part is slowly varying. Okay, so what we can think of is that this part is almost like an envelope, whereas this part is like a carrier. We have looked at this concept before, and what we have is that since this is slowly varying, so you can think of it as like a wave like this, where the wave is rapidly varying in the z direction, but it's slowly varying in the transverse direction, plus maybe whatever leftover z variation that it has. Okay, so this equation can be approximated, or this expression can be approximated as such, and there's no actually there's no approximation being made. I'm just postulating that the solution looks something like that. And since this is valid for x, y, z component, I can focus my attention to the x component first, for instance. Okay, and let's assume that the x component is described by a slowly varying function psi. Okay, multiplying by this rapidly varying function e to the minus j beta z, and this is rapid. This is slow. And I'm interested in the high frequency solution, as this section of the lecture is. So beta is omega over c is going to be very large when omega goes to be very large. So I'm interested in the high frequency approximation of this. Let me plug this into that equation over there. And if just take the x component of this equation, I would have the fact that the Laplacian of ax, okay, xyz, would be equal to the partial square x squared plus partial square y squared plus partial z squared times psi of r e to the minus j beta z. Okay, and let me pay special. Okay, can you hear me now? Or?
Yes.
Okay, my Surface tablet just went dead. And it recharges itself right now. Okay. So if I plug this into the first term over here, I will have this over here. And let me pay special attention to this partial square, partial z squared, because one term is slowly varying and the other term is rapidly varying.
You are not sharing screen.
Oh, sorry. I guess it stopped sharing after I got locked out. Okay. Okay, so one of this is going to be slowly varying, the other one could be rapidly varying. So let me focus on the second derivative of z first, and then worry about the others later on. So if I were to do this, then let me use a new slide to describe this. Then I will have partial square, partial z square psi of r e to the minus j beta z. And then using the fact that if you have a second derivative of a product of two functions like fz, gz, if you take the second derivative of this, it is going to be the second derivative of the first term times g of z, and then you have two second derivative, two first derivative, followed by the second derivative of the last term. this rule that we all know quite well, and we apply this rule, then this would become equal to the second derivative of the first term, okay? So I will have partial square, partial z square psi of r e to the minus j beta z. And then using this term, I would have 2 partial z psi of r. Okay, and then the first derivative of this term, which gives me minus j beta e to the minus j beta z. Then when I apply that to the last term, I would get something like minus 2 beta square psi of r times e to the minus j beta z. Okay, I will have these 3 terms. Okay, and I have these 3 terms, and I'm going to assume that beta is large. Okay, beta is very large. And then if I compare this term has beta square in it. So it's going to be the largest term when beta goes to infinity. And then I will have this second term. It has only 1 beta in it. Instead of beta square, it just has 1 j beta in it. It would be the second largest term. And then since I'm assuming that partial square, partial z square is small because this part is slowly varying, and this part is also slowly varying with respect to x, y, and z. Okay, so this part is going to be small. In other words, when I compare all these 3 terms, this is largest, the second largest, this is the smallest. Okay, so I can actually just throw this term out if I wish to, but actually at this point, I don't have to. I can actually plug everything back in there, and I make a mistake here, which is that the 2 shouldn't be there. There's no 2, okay? There's no 2 there. So when I plug this equation back into this expression, which is the first line of this equation over there, there's a beta square term here, and then there's a beta square term here. So this term is going to cancel the beta square term that comes from this term, because when I did this, I just was looking at the first term. I was just looking at the first term and looking at only the partial square, partial z square term. Okay, when I plug it back in, this term is going to cancel this term. So I'm left with this term plus these are the 2 terms coming from here. Okay, but this term is going to be small compared to the other terms. So if I were to do that, then the equation I have is that partial square, partial x square psi of r plus partial square, partial y square psi of r. I'm going to plug this in here and keep only the first 2 terms, and only keep the important term in the last term, okay? And then if I keep the important term in the last term, because this term cancels each other, only this term is left in the last term. So I'm eventually going to end up with something that looks like minus 2j beta d psi dz. Of course, there is a e to the minus j beta z outside, and all this should be 0. And then I can just throw this out. And now I have an equation for the slowly varying part of the function. This equation is Kodi, Paraxial wave equation. Okay, it is derived by assuming that beta is very large compared to the other variation. And this is how you should have this. Okay, any questions so far? So one thing to note is that this equation has second derivative in x, second derivative in y, but only the first derivative in z. Okay, so this paraxial wave equation is very analogous to what we call the Schrodinger equation, the Schrodinger wave equation. Some of you might have studied quantum physics before, and if you remember what the Schrodinger wave equation is, it would be something like this, plus something like this, and then is equal to I h bar partial t psi. Okay, so this is the Schrodinger wave equation for where you replace z with time. Okay, so you replace z with time in the paraxial wave equation, you get the Schrodinger wave equation. And for those who have studied quantum physics before, you might remember this equation, and they are very similar except for that you change the z derivative to a time derivative. Okay. Any questions so far? So you can draw a lot of inspirations by looking at the solution of Schrodinger wave equation, which is a very important equation, has been studied umpteen times over. And whatever mathematical advancement that you make in Schrodinger wave equation, you can pretty much transport those knowledge over to studying the paraxial wave equation. Okay. So what is the paraxial wave equation? It's essentially a wave equation where the phase is changing rapidly in the z direction. Okay, the phase is changing rapidly in the z direction, and that the other parts of the solution is actually varying very, very slowly. So in the paraxial wave equation, what you essentially have done is that you take the wave equation and break it into slowly varying part and the rapidly varying part. The slowly varying part satisfies this paraxial wave equation that we have just described, okay? Which is that okay? So to imagine what is happening with this wave is that you can think of it as a wave that is propagating in the z direction. The phase is rapidly changing in the z direction, but otherwise it's slowly varying in the other direction. Okay? In the transverse direction, it's very slowly varying. It actually is an approximate solution to this equation. Okay, it's an approximation of this Helmholtz wave equation that we have studied many times over. But we know that this equation has closed form. And you have found these closed form solutions yourself. For instance, we know that a spherical wave is a closed form solution of this Helmholtz wave equation. And an example of this is this one. Okay, when we have a point source on the right-hand side, this is a solution. This is a solution when the Helmholtz wave equation becomes inhomogeneous. Okay, but let's do a very interesting trick. How can we make the right-hand side 0 so that the solution that we have written down here is always the solution to this equation? Okay. Professor George Deschamps of the University of Illinois had a great idea. He said that, why don't I make R prime a complex number? Okay. Why don't I make R prime to be a complex number so that it's given by z hat jb. Usually r prime is x plus y plus z hat z prime. Okay, so r prime is just the location of the source. But let me be creative and make this source being located in the imaginary space. And let me have r prime be written in such a manner where j is an imaginary number. And if I were to plug this in this equation, and if I were to write this equation down and say that, well, let me be creative and just say this is r prime minus z hat jb. Okay, 4 pi r minus z hat jp. Then r and r prime are never going to be equal to each other. Okay, r and r prime are always going to be different from each other because r prime is imaginary. So if r is in the coordinate space, r is in the real space. So what you have then is that this quantity that you have is never going to be zero. It's never going to be zero, which means that you are never going to get a singularity. You're never going to see the singularity of the Green's function, which also means that the delta function that you have on the right-hand side can be set to zero because r is not going to be equal to r prime anymore. Okay, so you can actually prove by back substitution that if you were to plug this equation back into this equation, since r and r prime are never going to be zero, you're never going to see a source singularity. And this equation always satisfies the homogeneous Helmholtz equation all the time. Okay, does everybody catch that or buy that?
Yes,
So,
I have a question.
Yes, what is the question?
Are those r and r prime orthogonal to each other in on the imaginary on the complex value plane?
Well, actually, you cannot even say that they are orthogonal to each other because r prime is in an imaginary space now. It's a mathematical artifact, something that you do by mathematics, by making r prime into an imaginary number. You don't even have a real space equivalence of r prime. Okay, but I know that this equation, this expression, is still a solution to the Helmholtz wave equation. As long as r is not equal to r prime. As long as r is not equal to r prime, this is a solution to the Helmholtz wave equation when you have zero on the right-hand side. Okay, when we say plug this back in to this equation, we say that whenever r and r prime are not equal to each other, I should set the right-hand side to zero, and then we'll have the homogeneous Helmholtz wave equation to satisfy. And hence this expression that I have fictitiously created by Professor Deschamps, okay, would always satisfy the homogeneous Helmholtz wave equation. Can everybody catch that? It takes some imagination to catch that. Okay, can you accept that or not?
So without this maneuver, if r prime was kept at real space, that means there would be singularity and you can't set the delta function to zero, right?
Yeah, if r prime had been in the real space, okay, then the right-hand side would have a singularity in the real space. And this expression will also have a singularity, that when r equals r prime, this thing goes to zero, and this field is singular, it becomes very large. But if r prime is kept to be an imaginary number, okay, so the right-hand side is never going to have a singularity. Neither would this solution that you have plugged in here, and it will always satisfy the Helmholtz wave equation without a source point. Actually, the best way to convince yourself, if you still have been having trouble accepting this, is to convince yourself by back substitution, plug this equation back there, differentiate, and show that it always produces a 0 on the right-hand side. Okay? So can I move on and let you go home and test it out by back substitution? Okay, if you will allow me to move on, I just now claim that this is the exact solution to this equation. Okay, so which means that there is an exact solution to this equation. I can make this equation to become paraxial wave equation. Okay, I can make this equation to become a paraxial wave equation. This is an exact solution, and I can make it paraxial by putting my observation point to be very close to the z-axis. So if I take this expression that I have just created, okay, and then if I keep my observation point very close to the z-axis, then this exact solution would become the paraxial wave equation approximation. And we're just going to do that. And so I'm going to let this r minus r prime be equal to, mathematically, is defined by x squared plus y squared plus z minus z prime square, but z prime, as you know, is plus minus jb. Okay, that is what I have my z prime to be. Z prime, as you notice, is just minus jb. Okay, z prime is actually, let me correct myself. I should put a minus sign here. Put a minus sign. And then if I do that, then what I have is that this is going to be x squared plus y squared plus z plus jb squared. Okay, I'm going to have that, and I'm going to make a paraxial approximation to this expression, which means that I'm going to assume that x and y are small, z is large. Okay, so if I put my observation point over here, I'm going to make z very large and x and y to be very small. And I'm going to do a Taylor series approximation of this. I take this large, sorry, I'm going to take this large term outside. Okay. And then what I have left inside is 1 plus x squared plus y squared over z plus jb squared. I'm going to have this approximation. And then I can do Taylor series expansion now. 1 plus a small number. This is a small number. Because I'm going to assume that z plus jb is very large. And using Taylor series approximation, I can say that this is approximately z plus jb. And then multiply by this small number over here. Okay, I'm going to write really fast because there's no deep thinking here now. It's just straightforward approximations. And then you can have z plus jb plus x squared plus y squared over 2z plus jb plus ... Okay, this is just a Taylor series approximation. And when I plug this back in to the original expression that I had here, okay, then I should get an expression that looks like this. Okay, I should get an approximation that looks like that. And then I can say that that approximation would look something like this. Let me write it down. So then ax r, I'm just going to use this approximation into into this expression over here, I will get something that looks like e to the minus j beta z plus jb over 2 pi z plus jb, and then keep the phase term because this phase term is important. Okay, I'm going to keep this in the phase, and then I'm going to ignore it in the denominator as we have always done. Okay, the exponential term is important because this beta can be large. So if I keep it in exponential, then I should keep these small terms there as well. X squared plus y squared over 2z plus jb. Okay. In other words, I keep these small terms in the exponential when I plug it back in the exponential. And this biological argument should be the same as this equation, which is the paraxial wave approximation to that expression over there. Okay, this is the paraxial wave approximation to this function, and this is something that I have derived from an exact solution, and now I can compare the two. Okay, there is a beta z term over here, and the rest of that must be psi xyz. So I can actually infer what my psi xyz should be. Okay, you can actually go and do the inference. The detail is done in the lecture notes. It's just quite a bit of math. Okay, and very little physics. But then let me just write it down in full for you, just in case that you might be interested in this. Okay, if I were to write this down in full, then what I find is that psi xyz should be something of this form. A constant. The constant need not be the same as before. And then I can write this as z squared over b squared, because I can also write this as the magnitude times the phase. Okay, e to the j arctangent of z over b. And then I'm going to write this exponential function in terms of e to the minus j beta, a real part and an imaginary part. So what I'm going to do is actually to have this become small. Let me see, make it big again. Okay, so this becomes z squared plus b squared, and there's quite a bit of algebra that goes on here. Okay, and then e to the minus b beta x squared plus y squared over 2 z squared plus b squared. Let me tell you what algebra went in here. The algebra is quite straightforward because I have this 1 over z plus jb. Okay, with complex number algebra, this can be written as the magnitude square. Okay, the magnitude of this complex number times its space. Okay, and then you can write this as 1 over z squared minus jb over z squared plus b squared. Okay, you can write this as that by just completing the squares and doing something clever to the numerator and denominator. And then if you do that, then this can be written as, let me see, a magnitude square. And if you take the magnitude square of this, you will get something like, if we take out the b square, then I will have 1 plus z square over b square, square root of, and then with that, well, I'm not doing it in a very clever fashion, but you know how to do this. Okay, in order to find the phase, you'll find that the phase is something like exponential to the arctangent of z over b. Okay, you just take the real part, imaginary part, and compare that, you get this function. Okay, and then you plug that in, you get this kind of thing. And you do the same thing to this thing over here. Break it into a real part and imaginary part in this manner, and then you get all the algebra. Okay, it's just very tedious algebra that I'm sure you can do it at home. And you can do that on your own. Okay. So what are the physics that you can note here? The physics that you can note here is that this says that in the transverse direction, the beam is Gaussian tapered. Okay, after you've gone through the math, you try to elucidate the physics from the math. And what it says is that as you move in the x and the y direction, which is transverse to the z direction, the beam is Gaussian tapered. It becomes smaller and smaller in the exponentially Gaussian way. Okay, and there is a phase front that actually makes it look like a spherical wave. If you compare this with the phase front of the spherical wave, this has a certain radius of curvature. Okay, so you can actually get a radius of curvature from this wave front, and that radius of curvature is z squared plus b squared over z. Okay, I'm not going to go through the detail, but you compare this to the phase front of the spherical wave and get the radius of curvature of this phase front to be that. And then this actually just shows that it's Gaussian tapered. So the math is rather complicated, but finally, if you were to plot this wave out, it's going to look something like that. It has a waist. It has a waist because it's Gaussian tapered. Okay, it has a waist. And the waist actually becomes narrow at the z equal to 0 point. The waist actually spreads out and becomes wider and wider. And that is in agreement with what we have learned before. We have learned before that anything becomes like a spherical wave if you go far enough away from the source point. That means that if you look at this expression, and if you go far enough, and if r is big enough, r prime is unimportant, and this will just look like a spherical wave. And this is what the plot is showing, that the wave actually becomes like a spherical wave, and the waist of this beam, this Gaussian beam, actually becomes broader and broader. And if you think of this Gaussian taper as being a waist, you can change it. You can see that the waist is not a constant. Okay, the waist of the beam is not a constant. It's hard to see it right away, but if you stare at this equation and contemplate on this, you can see that the waist of the beam is being changing. And then there's a phase variation here too, that you can contemplate on the physics of it. So a Gaussian beam will look something like this, okay? And it is actually how a laser beam would look like out of the laser beam pointer. If a laser pointer, the wave that leaves the beam, the pointer, will look something like this. It's actually more or less collimated in the beginning, but as you go further and further away, the collimated beam is going to look like a spherical wave. Okay, and we also study something called the Rayleigh distance. You can say that the Rayleigh distance is the distance for which the beam remains collimated, and then after that distance, if the observation point has exceed the Rayleigh distance, then the beam starts to divert. Okay, so it turns out that this Rayleigh distance that you've seen in your homework is proportional to 1 over lambda. So when the wavelength is very short, the distance of collimation is longer. The Rayleigh distance is also longer. And the laser beam can get collimated for a longer time before it diverges. Okay, I'll let you contemplate on this physics more. But what I want to say is that solving the paraxial wave equation is an art and also a science. You can use the separation of variables to solve this equation. You can actually solve it like the Schrodinger wave equation. And it's been done quite a bit in the field. Okay, these are the solution to the paraxial wave equation using Hermite Gaussian polynomials, and then using Laguerre polynomials. And they are all done by using separation of variables. You can see a Gaussian beam here, a Gaussian wave, and then you can see that they have different kinds of phase variation. And these beams are very interesting. They actually look quite interesting. They look something like this. Okay, so if you look at these Gaussian beams, or they call it Laguerre Gaussian beam, I should put this in front of you. Okay, so if you look at these Gaussian beams, they have all kinds of patterns in the x and the y direction. And they have different kind of angular momentums, as so as to say, okay, because they will have very interesting x and y variations. If you look at the x and y variations, they're quite rich and interesting, and they can give rise to different kinds of angular momentum. Okay, as we said before, if you have a simple wave, say a simple wave just like that, this wave has an angular momentum in the phi direction. But a Gaussian beam is more complicated than that. It has very rich patterns and different kind of angular momentum. We call those orbital angular momentum. Okay, and orbital angular momentum is essentially due to the fact that the wave has x and y variation. And when they have x and y variations, just like anything that has x and y variation, they have momentum in the x and the y direction, and they can be combined to make orbital angular momentum, as they have done in quantum theory. If you study Schrodinger equation, you always hear about the term of orbital angular momentum, and also spin angular momentum as well. Okay, so this is the field, emerging field in optics. So I'd like to move on to talk about Rayleigh scattering. Rayleigh scattering by small objects. Okay, that itself is very interesting. So Rayleigh scattering is also a kind of high frequency scattering. The wonderful thing about Rayleigh scattering is that with this understanding, you can explain many optical phenomena around yourself, like the beauty of the sunset, the reason why the sky is blue and why are things green, and so on. Okay, why is the waterfall white in color, and so on. Okay, so what is Rayleigh scattering? Rayleigh scattering is scattering by small particles. So if you look at the water molecule is about maybe 0.25 nanometer H2O. And if you look at blue light, lambda is about 500 nanometers. So if you were to study the scattering of light by water molecule, is considered scattering by small particles, where the size of the object is much, much smaller than the wavelength. So you can think of light as being an electromagnetic field, and when the field impinges on this particle, the first thing it does is to polarize this particle. Polarize this particle and make it become like a dipole. And you have done this as the homework. Okay, so what you see is that this dipole moment, and this dipole moment is created due to the fact that this electric field would drive positive charges flow in that direction, and negative charges to accumulate on the other thing, and this makes it look like a small Herschen dipole. So it's so small compared to wavelengths, it's no different from a Herschen dipole. And the dipole moment is given by this. And that you can show that P is linearly proportional to the incident field. Okay. And this is called the polarizability. So essentially, in order to understand Rayleigh scattering, the first thing that you need to find is the polarizability of this small particle by the light impinging on that. And because the light wavelength is so long compared to the size of the particle, you can treat this as an electro-quasi-static problem. And you have done this in your homework. And since you have done this in your homework, the good thing is that I don't need to rederive the solution. Okay, I can show you that actually I like to mention that this was done by Lord Rayleigh. His true name is J.W. Strutt. Okay, but because it was a baron of some kind, who owned a huge piece of farm. He lived on a huge farm and lived like a lord. People used to envy him because he was a lord, as well as he has all the time he could to do science. He published over 400 papers. Okay. Okay, that's a good thing about it. And then I wouldn't I think we have studied this before, and let me just write down the solutions for you instead of having to derive it. And what we have derived before is that this problem can be solved, and that the dipole moment, if we were to approximate the current J, R is Z hat IL delta R, which is a Herschen dipole current, where IL is I omega QL. Okay, when we study Herschen dipole, we can show that the dipole moment P is equal to QL is given by 4 pi epsilon S minus epsilon over epsilon S plus 2 epsilon A3 EI. Okay, you have done this as a homework when you study nanoparticles. Okay, so then we just use this result and understand the physics. First, the light comes in, polarize a particle, makes the particle looks like a dipole or a Herschen dipole, and then this dipole would just radiate like a Herschen dipole because it's so small compared to wavelength. And the polarizability is given by this equation, that the dipole moment P is proportional to the amplitude or the incidence field. Okay, is this good enough? Any questions so far? I'm not going to the detailed analysis, but using the mere fact and the mere physics that the wave comes in, polarize the particle radiates like a Herschen dipole. Okay. So then we would like to know the far field of this Herschen dipole that is radiating. Okay, we know how to find its polarizability and the amplitude of this Herschen dipole. And then in the far field, then E, as we know, is J omega A minus gradient of phi, where A is the vector potential, phi is the scalar potential. And we have Lorentz gauge being used. And Lorentz gauge says that divergence of A and phi are related to each other. Again, this is the Lorentz gauge. And if I plug this in here, I will get the fact that this is j omega a. Sorry, this should be a minus sign here. J omega a minus 1 over j omega mu epsilon. Okay, gradient of the divergence of A. Okay, I would have that. Did I tell you right? Let me hope that is what. So I have this with Lorentz gauge, and then what I have then is that in the far field, gradient can be replaced by j beta. Okay, and for a spherical wave, it's just j beta r for spherical wave. Because when I'm far away from the Herschen dipole or the Rayleigh scatterer, okay, it's going to essentially see a spherical wave. Okay, and then if you plug that in here, then I find that E is approximately equal to minus j omega A minus beta beta. The 2 delta gets replaced by beta beta over beta square. Okay, and then I would have this dot with A because it's a dot product over there, and then I can show that this is equal to j omega A minus r hat dot A, because beta is r hat. And then we get the same result as we had obtained before. That in the far field, we need the theta component of the vector potential plus the phi component of the vector potential. Okay, and as long as we know the theta and the phi component of the vector potential, we know the radiation field of a Herschen dipole. Okay, so you can figure out the radiation of a Herschen dipole quite easily. That we have done before. Let me see. So I can do it more carefully if you want to. And what I need to do then is to first show that so how do I find A theta? Well, I can do it more carefully. I can assume that I have a Herschen dipole to begin with. If I have a Herschen dipole to begin with, then I know that A, due to a small dipole, is given by this expression, which I have written down before. Okay, that this equation we have written down many times over. E to the minus j beta r minus r prime. Okay, when we use this equation and plug in this Herschen dipole, for the approximation of the Rayleigh scatter, we get the fact that this has to be, because r prime is equal to 0, r prime is equal to 0 in this expression over here. I use the shifting or the shifting property of the delta function. I get mu IL over 4 pi r e to the minus j beta r. Okay, I get that to be my solution, and this again is writable as j omega mu ql over 4 pi r e to the minus j beta r. If I assume that I is j omega q, il is j omega ql. Okay, if I make this assumption, then the vector potential is given by that expression over there. And I know what QL is. QL can be done from your previous homework. You sort of found that the QL by finding the electrostatic solution. You can find the dipole moment of this dipole field, and that QL is given by this expression. And then you found that QL is given by that. And because of that, you find that A theta is the theta component of this, okay, of z hat. You convert this into a theta component and a rho component. So if you take out the theta component, you will get this to be j omega mu ql over 4 pi r e to the minus j beta r cosine theta. When you convert this z hat to a theta hat, sorry, it should be sine theta. Okay, it should be sine theta. And then e theta is minus j omega a theta. Okay, this is what we get from this expression over here. E theta is given to be that. And this dipole field does not have any a phi. A phi equal to 0. Okay, we have a phi equal to 0, and then you can find e theta, and you can plug this back into a theta and find what e theta should be. And you find that e theta is given by this rather complicated looking expression. I just write it down for you anyhow. Omega epsilon s minus epsilon over epsilon s plus 2 epsilon, okay, times a cube over r square, r, actually just r, sorry. Okay, you will just get this as your expression with the sine theta term out front. So e theta is going to be looking like that. Okay, and this is a spherical wave that emanates from this little dipole. And this is a Herschen dipole. And if you are in the far field of this Herschen dipole, you can use plane wave physics. Okay, spherical wave becomes local plane wave. So if you have a spherical wave, if it's far enough away, okay, if you're far enough, it becomes locally like a plane wave. And then you can use plane wave physics to figure out what the H field is. Okay, you can treat them as a locally plane wave. You can see that Hp is actually equal to 1 over eta E theta, assuming that if you have this being your coordinate system, this is x, this is y, this is z, and you can think of E theta as pointing in the theta direction, okay? And then you can figure out what Hp should be using a plane wave approximation for this thing emanating from there. And eta, of course, is this intrinsic impedance of free space. And then after using E And using H, you can find the complex power. Complex power is E cross H conjugate. Then the complex power will be pointing in the Z direction because it will be E theta crossed with HT will be something that points in the, sorry, why does it become so small? Okay, so it becomes something that points in the radial direction. Okay, E theta HT conjugate. Okay, it becomes that, and then this would just become the time average power would be just half E theta magnitude square divided by 1/8. You plug this in, you will get that to be your time average power flowing in the radial direction, and then you can find the total power scattered, okay, by integrating this over the entire angle, E theta HP star, and then it will be 1/2 eta, the entire integration of this E theta squared. Okay, so that's how you find the total power scattered by this small spherical particle. And it is quite a bit of plug and chuck mathematics and physics. So let me pause for a moment to ask if there's any question regarding this. So you can find you have all the amenities and all the things that you need to find the power scattered by this small particle. And then you can plug and chuck and do all this integration. The only technical difficulty is that you have to know how to do the three-dimensional integral over the angular sector. So this d omega, as you know, in spherical coordinate is r squared sine theta, sine square theta, d theta, d phi. Sorry, just r sine theta, d theta, d phi. Okay, if you remember that, d omega is r square sine theta, d theta, d phi, but d theta goes from 0 to pi, d phi goes from 0 to 2 pi. That's how you do this, the omega integration. E theta, you get from here. Okay, E theta you get from here. Why does E theta have to decay as 1/r? This is a physics question, a sanity check. Why does E theta have to decay as 1/r? Does anybody know? Why does E theta have to decay as 1/r? Anybody wants to volunteer a answer to this question? Why does E theta have to decay as 1/r? If your E theta does not decay as 1/r, it will violate a very important physical principle. What is that? Does anybody know? Why does the far field of a Herschen dipole have to decay as 1/r? Anybody? What about Ivan? Would you be able to tell me why the far field of a Herschen dipole have to decay as 1/r?
Well, I think, well, I see here a spherical wave, which is locally plane wave over there in the far field. So it decays as 1/r.
So why does the spherical wave have to decay as 1/r? I guess you can derive it by mathematics and show that it's a spherical wave, but there's also a very important physical reason for that.
Energy conservation.
Very good, excellent. Who said that? Is it Arjun?
Yes.
Okay, energy conservation. By energy conservation, the field has to decay as 1 over r. Because in the far field, we have plane wave physics. The H field is linearly proportional to the E field. Okay, so the power will be proportional to E theta square or HP square. And if you look at the power, the Poynting vector, it has to be proportional to 1 over r squared. So the power has to diminish at the rate of 1 over r squared. And why is that important? Well, what it says is that the energy has to decay as 1 over r squared because the energy going from one sphere to the next sphere has to be equal to each other. So this sphere, the first sphere, has the area of 4 pi r squared, 4 pi r1 squared. The second one will have a spherical area of 4 pi r2 squared, and the two areas have to carry the same amount of energy by energy conservation. So a spherical wave has to decay as 1 over r, and its total power has to decay as 1 over r squared. And then when you plug it in here, if you do this integral later on, you do it carefully, then this r squared coming from here will cancel this r squared. This r squared is due to the omega, is the increase in the size of the sphere as you do this spherical integration. And finally, this would be a constant. R squared and this r squared cancel each other, it becomes a constant. And hence this power scattered asymptote to a constant will become a constant eventually. Okay, and you can work this out. And there's a lot of plug and cut mathematics here. So finally, you find that PS is equal to 1 over 2 eta, beta to the 4th power. Okay, magnitude of epsilon s minus epsilon s plus epsilon with a 2 somewhere, and there should be a factor of 2 somewhere. Okay, square, and the a to the power of 6, r to the power of 2, ei, and then there's an r squared, so the r squared cancel each other. Okay, and then there would be an integration. You have to perform this integration. The phi integration is very simple because the problem is independent of phi. So the phi integration just gives you 2 pi. Okay, and then you have to integrate the theta integration. The theta integration gives you sine square theta 0 to pi. Actually, sine cube. I'm sorry, sine cube. The reason why it's sine cube is because there's a sine square coming from here. Okay, there's a sine square coming from here, and a sine theta coming from d omega. So finally, you have this sine cube integration. Okay, the phi integration gives you 2 pi. And I presume you know how to integrate sine cube. It's high school algebra. I actually outlined it in the lecture notes as to how you should integrate the sine cube. Okay, I give you the answer, but you can go and you can actually go and do this at home carefully. 4 over 3. So everything can be found in closed form. You can find this scattering cross section. Okay, and then there's something called a scattering cross section, which is the total power scattered divided by the incident intensity. This is like power, okay, or maybe just SI. Okay, the incident power that's coming into the scatterer. So this gives you the concept of scattering cross section. what it says is that the incident field intensity times the scattering cross-section give you the power scattered. So this is a physical meaning, a geometrical meaning that this plane wave coming in, impinging on this particle, which a certain cross-section area of sigma s, and it will intercept that power and scatter it everywhere. That is called the scattering cross-section of the particle, okay? And this scattering cross-section is proportional to PS. PS is proportional to a to the power of 6, but beta to the power of 4. Okay, what does that mean? That means that the power scattering cross-section is proportional to frequency to the 4th power. If you think of beta as being proportional to omega, it says that PS is proportional to omega to the power of 4. Okay. The reason why it's proportional to the power of 4 is because the scattered field is proportional to the power of 2. If you look at the scattered field from this Herschen dipole scatter, is proportional to the omega squared. And the reason that physicists like to give to this is because radiation is due to acceleration. Acceleration is due to d squared dt squared. Okay, dt squared, and we have dt squared, and you have omega squared. So this is a clear indication that the scattered field or the radiated field is proportional to the acceleration of the electrical charges on the dipole. Okay, that's why we have this beta to the 4th power dependence and omega 4th power dependence here. Okay, so let's go and explain why the sky is blue and why the sunset is red. So what the scattering cross-section tells you is that the higher the frequency, the more the scattering. That is just from Rayleigh scattering. Okay, the higher the frequency, the more the scattering. So if you have white light or sun ray that tries to reach your eyes, say if you are sitting on the Earth's surface, and then if you're over here, and then the sun is over here, and you don't look into the sun directly, the sun hits a water molecule in the air, and the water molecule scatters off the atmosphere, and those light reach your eye. And because the higher the frequency, the higher the scattering, blue light tends to be scattered more than white light or other lights. On the solar spectrum, you see a lot of blue lights being scattered into your eyes. That's why when you look into the sky is blue. Okay, any question on this? Okay, so blue sky.
I have a question.
Yes.
Why don't we see the light in violet or purple color? Since it's
I'll explain to you why you don't see purple in a little while. Okay, so by your argument, from Rayleigh sketching, we see that the higher the frequency, the more scattering there is, but it doesn't go that way. Okay, I'll explain that in a little while. And then, why is sunset so richly beautiful? Well, we have this Earth with a very thin layer of atmosphere, and so if you're sitting here looking at the sunset is just setting over the horizon. So the sun ray that reaches your eyes have to go through a thicker atmosphere. So by the time it reaches your eyes, all the blue and the white and the green lights have been removed. Only the long wavelength stays behind and reach your eye. Long wavelengths are red in color, like infrared. So something that is longer in wavelength, we call it infrared for that reason. So red color is on the other end of the spectrum with the longest wavelength, and those colors reach your eyes. Okay, so that explains why the sunset is so beautiful, so beautifully red. Okay, if you look the other direction, you see blue. Okay, and then you can also use Rayleigh scattering to explain why you can use the polarization of the light scattered from the sky to actually decide where the sun is. Because if the sun is coming in and polarizing the water molecules in the air, water molecules do not scatter isotropically. If you have a Herschen dipole, okay, it radiates in this direction. So by knowing your position with respect to the scatter, you can figure out where the sun is. I explain this more carefully in the lecture notes. Okay, so it is purported that the Normans, I did the Normans, no, the Vikings. The Vikings actually were able to sail to the Greenland without a compass. Unlike the Chinese, they never invented the compass, but yet it was purportedly said that they actually reached Greenland long ago without a compass. It was said that they used a sunstorm to navigate themselves, which is a kind of crystal. And why is the sky not purple? It's explained by Rayleigh scattering. So this is Rayleigh scattering over here. And if you were to study the scattering from a spherical particle, Rayleigh scattering is only valid when the particle size is much less in the wavelength. But as the particle size gets bigger or the frequency gets higher, then the scattering actually becomes stronger, but eventually it peaks out, it peaks over. And so it happens that this part of the spectrum is where it turns purple, okay? So if it goes on, the sky would become purple, but beautifully so, it did not turn purple. I don't know how many of you would have loved a purple sky rather than a blue sky, okay? Then the color turns this way, okay? So Rayleigh scattering and Mie scattering, that's something that I talked about in the lecture notes more, which is Rayleigh scattering versus Mie scattering. So as the frequency gets higher, the scattering is actually more in the forward direction. And there's something called the optical theorem that I don't have time to discuss. And you should read about it in the lecture note. It's a beautiful theorem, okay? It says that light scatters predominantly in the forward direction as the frequency gets higher. So it's unintuitive, but it is true. As the frequency gets higher, the scattering of the light tends to be in the forward direction. Okay, I explained that in the lecture notes. So I'll stop here since my time is up. Any questions? If not, then I'll let you go then.